Welcome to Higher Structure Seminar Series of Feza Gürsey Center for Physics and Mathematics. First of all, Happy New Year. I hope 2025 will be a better year, let's hope, let's say. Uh, and today, Mehmet Akif Erdal from Yeditepe University, Istanbul, will tell us about vibration category structures on monoidal slash enriched categories. We thank Akif for giving this talk. Please, Akif.
Okay, thank you, İrfan Hocam, for the invitation. The title is Fibration Category Structures on Monoidal and Enriched Categories. So, let me start by first page. There are various notions of fibration categories in the literature. Uh, there are Bauer's notions or other notions, but we will use Brown's version. It is the one of the first ones. A fibration, okay, that is called category of vibrant objects. Brown just called it fibration categories in his paper, 73 paper. So what is a category of vibrant objects? These are normally when you do homotopy theory, the original setting was model categories, but they are quite rare. They are not that abundant. Fibration categories, on the other hand, they are more relaxed versions and they are quite abundant. I mean, actually, any infinity category, infinity one category, or any quasi category can be presented up to homotopy by a cofibration category, dual of that. This is, I think, due to Carol Schumler's thesis in 2014. So, what's the category of vibrant objects? This is it's a category C together with two subcategories there, which contain all isomorphisms, so the core of C. And the category satisfies the 5 axioms listed here. First, it must have a terminal object, which we will denote by a star, and it must have binary products. And it needs the weak equivalences that the category V sub C need to satisfy 2 out of third axiom. There is actually a better version of this axiom called 2 out of 6 axiom, which guarantees in fibration category something called saturation. Also, we have fibrations and acyclic fibrations. So the fibrations that are also weak equivalences, they are called acyclic fibrations, are stable. I mean, the pullback along a fibration or an acyclic fibration always exists, and it is fibration. And if it is acyclic, then it is acyclic. So when we have a pullback diagram here, if this arrow is a fibration, then this F prime must also be a fibration in that pullback, and that pullback exists. And if it is an acyclic fibration, then F prime must be also an acyclic fibration. And one of the crucial properties is every object has a path object. That means the diagonal morphism for x to x times x factors through an object px, which is called the path space of x, such that the first arrow is a weak equivalence, and the second one, F, is a fibration. So these are path spaces are used for defining homotopy relation, just as usual. And the unique map from X to the terminal object must be a fibration. In other words, every object is fibrant, hence the name category of fibrant objects. This definition itself has many good consequences. Actually, all of them are mentioned in Brown's original paper. First, the homotopy category has a nice description. So it consists of, I mean, the arrows from A to B can be written as cosines. Sorry, like this. no, in other direction, sorry. Uh, so, and one leg of these cosipans must be a weak equivalence. Uh, so it admits, in other words, calculus of fractions. So if we have also 2 out of 6, then it means we have a homotopy category saturated. Uh, there is also Cameron's lemma, which follows from directly from the definitions. So a functor that preserves acyclic fibrations between categories of fibrant objects must preserve all equivalences. So it is a homotopical functor. And there is factorization lemma. Any uh, any morphism, so any arrow in C factors as a composition of a fibration with a weak equivalence. And there is also stabilization, which is a triangulated category that uh, there is a loop space object, and these loop space objects are obtained by taking the homotopy fiber of this morphism here, and it defines a functor from homotopy category to homotopy category of C, and this is a homotopy group object. So like H spaces in topological space, or for an analogy. And second loop space is a homotopy abelian. Sorry. Okay. So second loop object is homotopy abelian group object, and it gives us as the stable homotopy category, which is the when we formally invert that looped functor, is triangulated. So the objects, it can be constructed like this. Objects are pairs xn, and the set of morphisms from xn to ym is given by a colimit like this. And there is the shift, uh, and distinguished triangles are of this form here. So they appear in Brown's original paper, where here the map P is a fibration, and this F here is the fiber of this fibration. So we are particularly interested in category of fiber object structures in closed monoidal categories. So we start with this closed monoidal category that, and uh, we denote the tensor product like usual tensor, and one denotes always the tensor unit. This is symmetric monoidal. We always assume our monoidal always symmetric monoidal. Sometimes, I mean, that symmetric is within closed, but uh, in some sources we also need to mention separately. So on this closed monoidal category, assume that we also have a category of fibrant of object structure. So here we denote the internal home. We denote the internal home like this. This is the V with parentheses from A to B is the home's object, internal home. And if we want to denote the usual set functor, then we put a 0 in between. So we assume here in this talk, our categories are all concrete. So there is always underlying sets. There is usually when we, again, I said that usually homotopy theory is done by using, I mean, originally done by using model categories, and there is uh, something called monoidal model category. And in the definition of monoidal category, there is an axiom called push-out product axiom. And for closed monoidal categories, it can be equivalent to the pullback power axiom. So what is the pullback power? If we have a map from A to B and another map from X to Y, then the pullback power of F and G, so when you construct, so here we have, okay, there is the V, okay, sorry. This is V, A, F, sorry, VAG here, the vertical map, and this map is uh, V uh, FY. So when we take a pullback of them, when we take the pullback of them, we get a uh, sorry, okay. When we take the pullback of this, there is a unique map from VBX to this pullback because this square here formed like this is a commutative square. So by definition of pullback, there is a unique map. In a monoidal model category, if F is a cofibration and G is a fibration, then this map is always a fibration. And if one of them is acyclic, this is an acyclic fibration. And by using this information, we define a class of maps for a category of fibrant object. Normally, category of fibrant objects does not have the notion of cofibrations, but we we define a class of morphisms called pseudo-cofibration. So a pseudo-cofibration, so F is a pseudo-cofibration if whenever this G is a fibration, sorry, whenever G is a fibration, then VFG is a fibration. And if G is acyclic, then VFG is acyclic. So a pseudo-cofibration uh, is a map whose pullback power with fibrations is a fibration, and pullback power with acyclic fibrations is an acyclic. That is the, and they have similar properties as cofibrations. Of course, they are much weaker than cofibrations, but they have similar properties. This definition is given originally, the first document I've seen it, it is from Muro's paper, Fernando Muro, in 2015. It is defined in monoidal model categories for, of course, entirely different reasons. And he used push-out products instead of pullback powers, but in a monoidal category, they are, if it is closed monoidal, then we can just turn everything into pullback power. So anything, they are the same maps in that case. If we is a category of fibrant objects, full subcategory of fibrant objects in a monoidal model category, then any cofibration is also a pseudo cofibration by the push-out product axiom. But converse is not true. For example, the unique map from the initial object to the tensor unit may not be a cofibration, but it is always a pseudo cofibration. If you put, provided that we have these two properties. I mean, the initial object is initial in the enriched sense. It represents the terminal object. Sorry, co-represents the terminal object. So uh, this is the definition of pseudo cofibration. And in Muro's 2015 paper, he gave some properties of them. So pseudo-cofibrations are closed under composition, closed under taking push-outs, and closed under retracts. Actually, they are also closed under direct colimits under some properties. But since we are only working with fibration categories, we don't need that, so I don't write them. So we have a proposition here. If V is a closed monoidal category, that is also a category of fibrant objects, and assume that we have an initial object, which is initial in the enriched sense. That means it co-represents the terminal object. Then the following are equivalent for any object D in V. First, this is a pseudo-cofibration, so the unique map from empty set to the initial object to D is a pseudo-cofibration. It is equivalent to saying that the D tensor, this functor, which is a functor, let me, from V to V, preserve pseudo-cofibrations. And finally, it also, this is equivalent to this functor from V to V is exact. Exact means a functor is exact if preserves fibrations, acyclic fibrations, uh, pullbacks along fibrations, and terminal objects. So a functor is exact. So these are the functors between fibration categories. Did I mention it somewhere? Let's check. And no. Anyway, so that is the meaning of exact. So if object satisfy one of these equivalent conditions, then we call it pseudo cofibrant. Normally, there is cofibrant object, which means the map from empty set to D is a pseudo cofibration. Pseudo cofibration. Sorry, the map from empty set to D is a cofibration. Then it is called cofibrant in a model category. But here we don't have a model category, so if it satisfies one of these equivalent conditions, then we call it D a pseudo cofibrant object. And we denote the full subcategory of pseudo cofibrant objects in V by V sub P. And in V sub P, the Morose, I mean, in V sub P, the properties of mentioned in this proposition holds. So pseudofibrations are closed under composition. So the composition of two pseudocofibration is a pseudocofibration. They are closed under pushouts and closed under retracts. The proof is actually a formula dualizing this. We cannot do, since there is no lifting condition, etc., we cannot do Joyle-Tierney calculus, but we can formally dualize the proof of Muro and obtain this theorem or proposition. Maybe I can't just say proposition. And we will have uh, uh, even weaker version. This is due to Dwyer, Hirschhorn, Kahn-Smith's 2014 book, Homotopical Categories. A homotopical category is a pair, C and V, where C is a category, V is a class of, so a wide subcategory. So a subcategory that contains all identities uh, and it has a 2 out of 6 property that I mentioned earlier. So that means if we have a three composable arrows, and if compositions, this hooked compositions are weak equivalences, then all three and the composition of the three must be weak equivalence. So if two of them, if these two arrows are weak equivalences, then this is called the 2 out of 6 property. This is a little bit stronger than the 2 out of 3 property. A homotopical functor is a functor preserves weak equivalences. And in again, in from Dwyer, Hirschhorn, Kahn-Smith's book, there is the notion of deformation and deformation retracts of homotopical categories. So LF deformation is a pair Q and small q, so a capital Q and Q, where Q is a functor from C to C. Here C is a homotopical category, and Q, small q, is small q is a natural weak equivalence from Q to the identity of C. And a left deformation retract of C is a full subcategory where V sub Q of V that contains the image of a left deformation. And this functor by the 2 out of 3 property or 2 out of 6 property, this is homotopical. And also it follows from from the definition, homotopic category of V sub Q is equivalent to homotopic category of V. It is also proved in this book. And if you change the direction of this arrow here, then you get the right deformation, right deformations, and right deformation retracts. In 2006, Mike Schulman used it in his preprint to define monoidal homotopical categories. So if we, I combine his two definitions into one and try to just write it. Uh, yeah, I mean, the exact definition is not like this, but more general. So because I am only interested in the symmetric case. So if a closed symmetric monoidal category V, that is also a homotopical category, it's called closed monoidal homotopical category. If there exists a pair VQ, VR of left and right deformation retracts of V such that tensor is homotopical, so homotopical on VQ times VQ and sends VQ times VQ into VQ, the internal home is homotopical from VQ top times VR and sends this, I mean, its image is in VR when we are taking the source like this. And for every x for every x in VQ, Q1 tensor x from the Q applied to 1 tensor x to 1 times x, so this is isomorphic to x, is a weak equivalence. And if we replace the places of these two, this is also weak equivalence, but we are symmetric, so this is uh, uh, already true. And uh, for any y in V sub r, okay, this is the internal home here, but uh, the VQ1y is a weak equivalence. This map is a weak equivalence. So if we have such a structure on a if we have such a structure on V, then V is closed symmetric monoidal category, and the localization factor is lax monoidal. So by using that, we can, for example, use it for changing the base of four enrichments. So we have a proposition for symmetric monoidal categories with fibrant objects. Suppose that we have V is a symmetric monoidal category, and that which is also a category of fibrant objects structure on it, and there is a deformation retract VQ of V, in which every object is pseudo cofibrant, and since I mean, this is a pretty struck condition, but since one to one, but I mean, remember the tensor unit was already pseudo cofibrant, so it's actually uh, not that strong when you consider it. And for every D in V sub Q, these two functors are homotopical on VQ, then how we admits a closed symmetric monoidal structure. So, I mean, these two are enough to have, I mean, VQ, VR, when we choose VR as V, satisfy these four properties. You can think this V sub Q and V sub R here as cofibrant objects and fibrant objects, and these maps as cofibrant and fibrant replacements. So okay, so we continue with enriched setting. Actually, this is, I mean, all of these things, almost everything except the last proposition. I mean, the pseudo cofibers, etc., can be defined similarly for enriched setting. But I will talk not on them, but for construction of a general setting for enriched a category of fiber structures obtained from uh, co-representable functors, because there are many examples of it. I mean, much of the proofs are quite easy, quite formal, but the examples are quite abundant uh, in this setting. So we start with, again, V is symmetric monoidal category. V is a symmetric monoidal category and a category of fibrant object structure. And you can assume that they have I mean, some good limits and colimits in the enriched sense. So required limits and colimits in the enriched sense. So definition, we say a full subcategory A is so of V is colimit dense if every object of V can be obtained as a colimit of a functor into A. So in other words, if V is generated by objects of A under colimits. Uh, so then we call a colimit dense subcategory. For example, if we take I mean, for every V itself uh, is colimit dense in itself. This is trivial true, but we have non-trivial examples as well. If V is a topological spaces, that means, I mean, compactly generated weak house of topological spaces, so which is the ideal setting for homotopy theory, uh, classical homotopy theory of topological spaces. If V is top, we can choose A as category of compact, full subcategory of compact Hausdorff spaces. And since every object is compactly generated, so any object in V in top can be written as a colimit of objects in comp. Or we can take the category of simplicial sets and uh, choose A as the full subcategory of uh, simplices, simplicial simplices, delta n, which are these representable functors, in other words. And it is actually true for every functor categories. I mean, representable functors generate the functor category under colimits, and colimit is taken over the category of elements. Or there is Smith's delta generated spaces, for example. If we choose top delta, then the full subcategory of simplices is we can choose the full subcategory of regular, I mean, usual and simplices. Then this is uh, this is a I mean, top delta is generated by A in that case. I mean, examples are quite a lot for these kind of uh, categories or pairs. So let C be a V-enriched category. Let me remind you what is power. Sometimes it's called cotensor. So for every X in V and B in C, the power of B by X is an object pitchfork XB. Sometimes it is written, actually more generally, it is written like this, BX, such that uh, there is a natural isomorphism like this. So we have a lemma here. If we have a V-enriched category that is powered over a colimit dense subcategory, then the co-representable functors preserve limits. So limit that exists in C. So limits here is sent to a limit here. So I will just give a brief sketch of this lemma. If you choose a functor, it should be F. So if we choose a functor uh, from a small category I to C, such that the limit exists, so L is the limit, then we have a sequence of bijections of the underlying sets. So for any X in A, we have a sequence of bijections. So this is due to the isomorphism here of the powering. And powers always preserve limit, so that limit goes outside. And set represent, I mean, the representable, co-representable that goes to set always preserve limit, so that limit goes outside. And we again here we can use the isomorphism again object wise, and we have an isomorphism like this, and then since this is v sub 0, we can just put that limit inside. So this is true for every x. So if we write y as a colimit, then colimit of elements. So for any x in A, we have an isomorphism. An isomorphism like this. So an isomorphism in between. So any y can be written as a colimit of functor into A. So if you put right colimits here, you will see that they go out as limits and uh, go inside. I mean, back by using. I mean, by using this isomorphism, we can obtain an isomorphism like this. Yeah. Uh, by unit lemma, the uh, proof follows. I mean, since the set representables are always there is always a bijection, natural bijection between them. So everything here is natural, by the way. We have these two objects must be isomorphic. So we have F here, stellated accidentally. Yeah. So this, I mean, this completes the proof. And we have a lemma here for path spaces. Let V be a closed monoidal category and a category of farthing object structure with a category of farthing object structure on it. And C is V enriched and finite complete category. Assume that uh, and C is also satisfy the condition of lemma. So it's powered over a polylimit dense subcategory. And assume that for any object y in C, this association is functorial. So path space of the home objects are functorial. So it's a functor of, I mean, sending x to P of C, x, y. And this functor is representable by an object in A. Then uh, there is a factorization of the diagonal morphism like this, where V is a weak equivalence, F is a fibration. So the W is a weak equivalence, F is a fibration. So if star holds, for example, if V has functorial path object, so we have a path object functor, which is, so I mean, this star holds if, for example, V has a functorial path objects, which is co-representable. So if we have a path objects of this form, then uh, star always holds. So in that case, uh, if y is powered by b, then we can choose the path object p sub y as the powering of y by b. So in that case, I mean, we can define the functor f sub y like this, which is representable by this object. Sorry, co-representable by representable by this object. So we can choose p sub y as the power, and we get a path space of y in that case. And there is another way of another way to obtain star. Actually, if we have our category satisfy the interval condition, then we have path object is a representable functor. So what is the, I mean, this happens, for example, in many of the known examples. So if the tensor unit, codiagonal of the tensor unit exists, so I mean, we have here one coproduct one. So this is the coproduct in the enriched case. I mean, it represents the uh, so this object co-represents the x times x. For example, the functor that sends x to x times the diagonal. So if there's a factorization like this, where p is a weak equivalence, and sorry, p is an acyclic fibration, and this j is a pseudo cofibration, then we can define p as the internal home of uh, with I. So this defines a path object functor. Uh, so in fact, uh, if we just apply with y to this sequence, we obtain, so v 1y is just isomorphic to y, v 1 coproduct 1y is isomorphic to y times y, because this is the this is coproduct in the enriched case. So we can choose py, we get identify py like this, and here the first map is weak equivalence and this map is a fibration. Because remember, definition of pseudo cofibration, uh, it sends, I mean, when we take home with pseudo cofibrations, it sends to fibration. So if the tensor unit is the terminal object, for example, if D is Cartesian closed, then this I is often called interval object. So it is the most, I mean, the plane interval object. So, and we have a theorem. This is the, okay, this theorem has many examples and applications. So let V be a closed monoidal category with a category of fibrant object structure on it. And let C be a finite complete category. So it has all finite limits. That is enriched over V and powered over a colimit dense subcategory A of V. If if for any Y in C, the condition star is satisfied, so we have this functor is representable, then C admits a category of fibrant object structure where F is a weak equivalence whenever the induced map on co-representables is a weak equivalence, and it's a fibration whenever induced map on co-representables are fibration. And remember, interval condition imply the condition star here. So we have many examples. We will give 5 of them here. You can increase the number of examples, by the way. I mean, consider one of the following categories. So Ban is the category of Banach spaces and weak contractions. They are called short maps. I will just call them short maps. Banach algebra is the category of Banach algebras and short algebra maps. So this is actually the category of full subcategory of monoids in Ban with respect to the projective tensor product. C-star algebra is category of C-star algebras. So C-star algebra is a Banach algebra with a involution satisfying star identity. And let met be the category of metric spaces and again short maps. We choose short maps because it has many advantages over. Sometimes actually short maps are called metric maps. So and alt alt alt sub R is category of R algebras and algebra homomorphisms, where R is any ring with unity. So if we choose V as top, A as category of compact, I mean the full subcategory of compact hours of spaces, and C one of Banach, C-star or C-star algebras or metric spaces, then we have a functor. In each case, we have a functor from C to top, which sends an object with, if we choose met, then it's metric topology. If we choose three of them, they are norm spaces. It sends an object to the norm topology. So if we choose one Banach or Sister algebra, then this is the norm topology functor. And if we have met, so we can always say the metric topology functor. But anyway, uh, so we can topologize the map CAB, the home set in C in each case, uh, by the subspace topology of the compact open topology between FA and FB. So, and we choose short map, so this is a closed subspace of this with subspace topology. This makes it a closed subspace of top FA, FB. So C is top enriched. So I mean we can define enrichment like this. So the composition becomes continuous, etc. It requires all the properties. And if we choose a compact Hausdorff space, this is also a well-known, but if we choose a compact Hausdorff space and any object, for example, any Banach space or Banach algebra or sister algebra or a metric space, then we can uh, define an object, I mean, define a structure on the set of continuous maps from X to B so that this is an object in C. So for example, if X is a metric space, then we can make the set of continuous maps from X to B a metric space. Remember here, X is compact Hausdorff. So it automatically has a metric space structure with the submetric. Similarly, if X is a Banach space, then we can define a uh, subnorm on it, and it automatically becomes complete because X is compact Hausdorff. And if X is a Banach algebra, this has Banach algebra structure. Algebra structure gives the one. And if X is a C-star algebra, then this also has a star operation. The involution is induced by the involution of B. In each case, it defines a powering because it follows from CAB being a closed subspace and top is Cartesian closed. And topological spaces has an interval object, the usual interval object, 0, 1. So it's a interval object. If it has an interval object, it satisfies the condition star. So the theorem applies in all four cases. So that means uh, Banach algebras, sister algebras, or metric spaces, they are all categories of fibrant objects uh, where weak equivalence and fibrations are created by co-representable functors. And the first one, sister algebra case, is actually done by Uwe Otkombayer in 2010. And Banach algebra case follows from Anders and Grodal's preprint in 1997. The metric spaces, they don't appear anyway, but for the metric spaces, there is no, I mean, it doesn't follow from them, but uh, it also follows from, I mean, it is kind of new, maybe. Uh, of course, the metric spaces as a category, it is not a very nice category. It doesn't have even coproducts, so uh, uh, none of them. Okay, the metric spaces does not, I mean, cannot be extended to a model category. Actually, none of them are full subcategory of fibrant objects of a model category. Uh, I mean, the sister algebra case is proven in this paper, and these inclusions are exact because they are both they have left adjoints, so they are all homotopical, and uh, these left adjoints actually are enriched left adjoints. So because of that, we can use Uye's result to show that these are also not full subcategory fibrant objects in a model category. And the other example is usual, I mean, for R algebras. First, we can define okay, Cortinas and Tom defined in 2007 uh, an R algebra like this. This is the polynomial algebra quotient out by this. And we can, by using this, uh, they define a simplicial set enrichment uh, where home objects, the simplicial sets at nth level sent are defined as the set of algebra maps from A to B tensor uh, Z to the Z to the delta. So and also there is a again in their paper they give a construction. They call it B to the delta n, and this defines a powering. They also show it. So the category of R algebras are simplicial set enriched and powered over representables. Simplicial category of simplicial sets has an interval objects. So delta one is an interval object. So theorem applies R algebras in that case. Actually, it applies in a weaker sense because not every object in simplicial set is fibrant. So it gives us not a category of fibrant objects, but a prefibration category. But there are also enough settings to mention some of the applications. There is also a covariant version of this. It can be given trivially, but there is also a more sophisticated version of the equivariant versions. I mean, there are two equivariant versions. I'm not giving the first one. Uh, Let G be a group, V be a closed monoidal category with a category of fibrant object structure, just as before. C is V enriched and powered over a colimit dense subcategory. And we satisfy the condition star in the previous theorem for path objects and define the category of G objects in C as the functor category from one object category for the group to C. So this is the category of G objects in C. So I mean G objects with a group action, in other words, with G equivalent maps. For each AB in C, we can define a GV enrichment. So here, if V is closed symmetric monoidal category, then GV is also symmetric monoidal, actually closed symmetric monoidal, but we only need symmetric monoidal for in that case. So GV is symmetric monoidal. So define GCAB as follows. This is the set of all, I mean, the object CAB. Remember, we choose concrete categories to work with. So uh, this is an object in V, and we define the action as the conjugation actions, the conjugation action. So it actually, let me just describe it. CAB to CAB to CAB. So in the, okay, this is CA action by G. This is CA action by G inverse. Sorry, in this first part, G inverse B. So composition gives a G action on CAB by conjugation, usual conjugation action. You can think about think it as the conjugation action on the underlying set. The G fixed points give the equivariant maps in that case. So this makes GC a GV enriched category. This is actually given in Reel's book, 2014 book, Categorical Homotopy Theory, as an example, in one of the examples. And we have the equivariant version of the theorem given previously. Let's start with, let F be a family of subgroups of G satisfying this property, that for every subgroup in this family, the H fixed point exists. So in this case, if A to the H exists, then any conjugate. I mean, if H is in F, we can just put any conjugate of F. H is in F, so it actually gives a family in the usual sense. And for every A object A in GV, sorry, okay, sorry, uh, A to the H fixed points for every A in GV. Then GC, the category of G objects in C, can be made into a category of Fibration objects where F is a weak equivalence or where F is a weak equivalence or fibration if for any H in F, the fixed point, sorry, sorry, this should be for any H in F and for any D in uh, GC, just, okay, this map, GC bar D F H is a weak equivalence, respectively fibration. Sorry. Uh, so, I mean, the induced map on the, remember, the induced map on this here, that bar here means that, so let me write here. So GC bar DF is a function from or arrow from GC GC DA to GC DB. So there is the conjugation actions on both of them. So on their fixed points, the induced maps must be weak equivalence, and so the weak equivalence created weak equivalence and created by weak equivalence and weak equivalences and fibrations are created by these kind of maps. Sorry for the mistake here. So this is a so this theorem says that the category of G objects in C is a category of Fibration objects where these maps are so weak equivalence and uh, fibrations are created by these co-representable functors. And why we choose this? Because it has nice applications. First, I will give the examples. Category of G Banach spaces, G Banach algebras, and G sister algebras, G metric spaces, and G algebras have these properties. Immediately follows that they are categories of Fibration objects in this sense. And like algebra, the category of algebras, this is actually prefibration category, G algebra R, because it is enriched over G simplicial sets, which is not I mean, in which there are objects which are not fibrant. So let me talk about the applications, mention some of the applications. The first application I will mention is actually due to Uye's paper. The category of KK is triangulated. So the category KK can be defined as objects as separable sister algebras. Here we assume they are also unital, and morphisms are, for convenience, morphisms are from A to B are Kasparov AB bimodules divided by the homotopy relation. But there are many alternative ways to create that KKAB. One of them is Kuntz picture for KK theory. So in this picture, it is due to, I will give in the references, Kuntz paper in 1987. So here QA is the kernel of the codiagonal, and K is the compact operators, C-star algebra of compact operators on a infinite dimensional Hilbert space, and this tensor product is projective tensor product, so it can be defined like this, and this square brackets mean the homotopy classes of maps. And this homotopy relation is actually coincide with the path homotopy that comes from the category of fiber object structure. And this KK, this is a homological functor from, so I mean, this functor here, KKA, is a homological functor. So by using this, we can define a, I mean, actually, Uye defined a category of fiber object structure on this category KK and show that KK is a triangulated category. And it can also be extended to GKK. So the category of, I mean, the equivariant version of this thing, the category of equivariant Kasparov's K theory. Again, this can be done by using equivariant version of Kunz picture, which is due to paper by Phillips in again 1987. And the equivariant version is given by a preprint by Bunke, Lant, and Engel. I will give it in the references. And we can also, by using the prefibration category structure on algebras, we can show that the small kk is a triangulated category obtained from the small stable homotopy category of a category of fiber objects. Here, small kk can be defined like this. It is the algebraic K theory, bivariant algebraic K theory. It's defined by 2007 Cortinas Tom's paper, and it can be I mean, we can create a category of fiber object structure on small kk by quotienting the category of fiber object structure on algebras that we actually prefibration category structure on algebras that we just mentioned in the examples. Here, the relation is f is equivalent to g if and only if the induced maps on algebraic K theories are the same. This functor is homological, and due to a result by Uye, this fibration category on algebras of R can be reduced to this quotient category. And it also given in Cortinas Tom's paper that there is a loop space object, and it satisfies, the loop space satisfies this property. So this is actually already a stable category. So this means OKK is triangulated. And this recovers the result by, I mean, the KK is triangulated, in other words, because because the definitions of weak equivalences here. So due to result by Cortinas and Tom, okay, this recovers the result by coordinate Cortinas and Tom, which says that the category of category KK is triangulated category. Equivariant version is due to Ellis, Johnny Ellis paper in 2014 paper, and it can be also recovered by using the category of fiber object structure, sorry, prefibration category structure on, so described here, on G algebra R in the same way. So GKK is triangulated category obtained as a small stable homotopy category of fiber objects. So maybe that is all for, I mean, that's all. Thank you for listening, and thank you for patience. And here is some of the references I mentioned. I also, maybe I should add that there is also my 2000 and here fibration category structures induced by enrichments. It is Recent people. Okay, thank you for listening and
Akif, thank you very much. Any questions or comments? So you developed a theory which extends these recent of things about KK theory by
yeah,
Cortinas, and so
yeah, they unify. I mean, it's a kind of
unification kind of.
unify it by using enrichments.
So what is your plan next in your study?
Uh, in, I mean, I actually want to find more examples. Maybe, and I want to also prove some results about how to extend these category of fiber object structures to model category structures, maybe, or use them to create some model structures on, I mean, some of the categories I work with currently. So, but I mean, this is quite easy to obtain. I mean, you just need an enrichment and a powering of some objects over some objects. So they are quite abundant.
Yeah, wonderful. Uh, any questions or comments?
Yeah, I'm wondering if there's a special case for like generalized rings, enrichments of generalized rings, like R modules for a generalized ring.
Uh, I I am not sure, but I mean, of course, there might be. I mean, that you can define enrichments over sequential sets, maybe, or sequential abelian groups. Uh, uh, you mean R mod category of R modules, right?
Yeah, sure. For a
Or
generalized
yeah,
ring or
uh,
like a simply
but I
ones.
haven't encountered yet.
Okay.
I actually the main motivation actually comes from this paper. Uh, I mean, so I was reading that, and uh, I saw that they come from enrichment, and it can be generalized to many other settings. So I decided to work on that. But
Very
of
interesting.
course, examples are quite abundant in that. I mean, also this has very nice properties as well. For example, if it is enriched over, um, I mean, if the enrichment is over a full subcategory of monoidal model category of fibrant objects, so full subcategory of fibrant objects in a monoidal model category, then the homotopy category uh, can also be given very, I mean, the home sets can be defined very efficiently like this, for example. If it is, for example, in the top case, so CAB is top star top AB. Sorry, ho, so homotopy category. Yeah.
Uh,
Or I mean, if it satisfy very mild under mild conditions, we have or CAB is if in the case when terminal object is the transfer unit, we have OV CAB. Sorry, this should be CAB.
I see. I see.
So so it actually, I mean, if it is just a category of Fibron objects, then we have still zigzag here. But in this case, we don't have any zigzags. It's also very, it is much nicer.
One more
Under
question. So your object CAB is a generalized space. Is that right?
I mean, if there are any, uh, I mean, if C is any category of Fibron objects obtained in this way, and we satisfy some properties, and we terminal object is the tensor unit in V, and the homotopy relation uh, satisfy some mild condition, then we have this identity. Uh, Here C is any category. And by the way, for example, topological vector spaces can also be an example. I also plan to work with, İlhan Hocam, you ask maybe stratifications or some filtered or stratified objects in uh, such categories.
Very interesting. Yeah, very good. Yeah, Akif, thank you very much. So we will meet 2 weeks from now. And uh, again, Happy New Year. And I'm closing the recording now.